Quantum computing in the 21st century uses the quantum mechanics of the 20th century to do computations using an entirely new class of algorithms. While their domains of application are somewhat narrow, in theory you might be able to run a web browser on a quantum processor someday, but it would still be silly. Quantum algorithms on quantum computers will completely revolutionize many fields of science and technology. Google began seriously investing in quantum computing in 2013 with the creation of the Quantum AI Lab. Initially, this was an investigation in partnership with NASA of the possibilities of first-generation quantum annealing technology using a D-Wave machine. But Google's vision of using quantum technology for artificial intelligence applications led us down a different road. In 2014, we started work on fully programmable quantum processors based on superconducting quantum devices. Since then, the Google Quantum team has racked up a number of firsts and world records in quantum computing. The first successful demonstration of a quantum machine solving a problem faster than the world's largest supercomputer, literally 1 billion times faster. The first quantum computing simulations of molecular behavior close enough to model isomerization, the process by which molecules of the same compound take on different shapes. The first instantiation of a quantum time crystal in quantum software. But the real objective of the Google team is to build a quantum computer large enough and reliable enough to solve real-world problems with quantum algorithms. Quantum computers are not faster than traditional machines. They are different. We talk about quantum speedup as the advantage that quantum algorithms have over what the quantum community refers to as classical algorithms, those that run on conventional computers. Some quantum algorithms are said to have exponential speedup, while others have only polynomial speedup. In talking about quantum computing, it's important to understand what this really means. It's not so much that quantum computers speed up as the problems get bigger. That would be pretty cool, but also suspiciously like magic. It's that for these classes of problems, the best non-quantum algorithms that we have will slow down exponentially as the problems get bigger, while the quantum algorithms do not. It's just easier to say exponential quantum speedup than it is to say quantum avoidance of exponential slowdown. However you look at it, the important thing to notice is that the advantage of the quantum algorithm is mind-blowingly huge for really big instances of the problem, but much less so when the problem is small. We can use today's small quantum computers to prove that the algorithms work, but the scale of today's machines just won't let us get far enough up the curve to make a practical difference. The nonlinearity of scaling pretty much means go big or go home. That's one reason Google focused on scalable quantum architecture and large machines, but there is another. Quantum information is fragile. We talk about quantum bits, or qubits, as the unit of quantum information. A qubit will always measure as 0 or 1, but between measurements it encodes a more complex and subtle state, with probability amplitudes that determine the likelihood of seeing 0 versus 1 when it's measured, and a property called phase that does not directly affect those likelihoods, but which can be manipulated in ways that do. Qubits can be deliberately entangled, meaning that the results of measuring one affect the quantum state of others. Much of the power of quantum computing comes from the ability to manipulate entangled states. But the universe is a messy, noisy place. We mechanically isolate our quantum processors from vibration, and for the sorts of systems that Google, IBM, and others are building, cool them down to close to absolute zero. But so long as the quantum state is connected enough to the rest of the universe for us to manipulate and measure in time, often in very little time, noise will perturb the quantum state, and it will decohere. Further, our manipulations of qubits will rarely be absolutely perfect. Even with the remarkable advances in precision electronics and photonics that have made today's early quantum computers possible, after some modest number of operations, fewer than 100 operations with current technology, the accumulated errors will render the computation meaningless. To perform large quantum computations, we have to be able to correct or otherwise mitigate those errors. And quantum mechanics doesn't make that easy. Under the rules of quantum mechanics, it's not possible to duplicate the full state of one qubit in another. We can't make backup copies. Quantum error correction involves algorithms that use collections of physical qubits to encode and correct each logical qubit's worth of quantum state for a computation. The more reliability we want, the greater the redundancy required. With near-term technology, error correction of the sort required to perform meaningful and useful computations could easily have something like 1,000-to-1 overhead. We sometimes talk about quantum error mitigation instead of correction as a lighter weight but less universal alternative. It's a topic of active research, but in theory and more so in practice, there are serious limitations to where it can be used and how effective it can be. I tend to think of them as analogous to the transformations performed by optimizing compilers for classical computers. They're generally useful, but only occasionally transformative. So between the fact that the real benefits of quantum computing are only delivered when solving really large problems, where the quantum speedup factor is big enough to matter, and the fact that every logical qubit in these computations may have to be implemented by hundreds of physical qubit structures on chips, it's pretty clear to Google that generally useful quantum computers will require large numbers of physical qubits, perhaps on the order of 1 million. Getting there from today, where the largest generally programmable quantum processors are operating within on the order of 100 qubits, seems like a daunting prospect, but it's probably worth noting that the semiconductor industry managed to get from solid-state memory chips with tens of bits to multi-megabit chips in roughly a decade. Google's quantum computing roadmap is a long path with many challenging milestones. The main one we are working on today is demonstrating that error correction actually works. Not only must the algorithm execute on a quantum device, but we need to show that the robustness of the logical qubit increases as more quantum resources are used, despite the greater probability of an error happening somewhere with the larger number of qubits involved. Then, we must demonstrate that this can be applied on multi-chip modules and then multi-module systems that will scale towards a 1 million qubit machine. What we actually build may not look exactly like the artist's sketch here, but it captures the scale of our ambition. So, how does this relate to the world today, and in particular, how does this relate to the climate crisis in which the world finds itself? The news there is both tantalizing and frustrating. The industrial production of ammonia for fertilizers today uses an old and well-understood process, the Haber process, that consumes more than 1% of the world's total energy use and contributes roughly 1.5% of all CO2 emissions worldwide. It's a brute force technique involving high temperatures and pressures. Yet, nature manages to perform the same operation, fixing nitrogen from the atmosphere, at standard conditions of temperature and pressure using a complex biochemical process. We've identified the molecule at the heart of this process and nicknamed it FEMOCO, but we don't really know how it works. If we knew, we might be able to develop designer catalysts to achieve a similar trick. It's not a huge molecule, but the quantum structure that governs its behavior is big enough for the exponential explosion in classical computing resources required to model it to have rendered the problem intractable. There are quantum algorithms that might unlock the secrets. They would require only a few hundred qubits, but they would need to be stable, error-corrected qubits. They need tomorrow's machines. Similarly, researchers in carbon capture are seeking ways to remove carbon from the atmosphere after it's been released by the burning of fossil fuels. Ideally, to create a closed-cycle carbon economy based on recycling recaptured carbon. Catalyst molecules to fix carbon won't be the same as those that fix nitrogen, but the principles are similar. Researchers in this domain have told me that for them, a few hundred sufficiently reliable qubits would suffice to simulate the carbon-fixing capabilities of newly imagined molecules. Another point of impact for quantum technology on climate and the energy economy is in battery design. We know how to make reasonably efficient batteries for vehicles, but some of the materials required are derived from natural resources that are scarce or otherwise constrained in their supply. Battery designers need alternatives, but the behavior of new potential cathode, anode, and electrolyte materials must today be determined experimentally, which is labor-intensive, slow, and expensive. Quantum molecular simulation has the promise to speed up the process of screening candidate compounds, helping to identify compounds that could be produced more easily or with less environmental impact. As with the catalysts for fixing nitrogen and carbon, these simulations may not require 1 million qubits, but they require substantially more than we can operate today. So quantum computing is very, very relevant to world climate, because it has the promise to let us figure out both how to dump less carbon into the atmosphere and how to take it back out again after we've dumped it there. And these are good things. We should do them. And I think we will. But getting quantum computing technology to the point where this science can be done, and turning that science into infrastructure at the massive scale required, will take years. Quantum computing will be a big help in the long term, but we must not think of it as a magic bullet or use it as an excuse to do anything less today.